Good afternoon, ladies and gentlemen. My name is Jie Longjun, and the topic of my presentation today is the discovering potential of multi-task detector in neutrino EM properties. This is a collaborative work. The authors include my advisor, Professor Deng Junhui, and Professor Liu Shenfang, Professor Jixin Chan from Tsinghua University, Professor Wang Zijing from SNICA, along with Dr. Wu Zipan, Dr. Mukesh Pandey, and Dr. Lakwinder Singh. Okay, so I shall thank them in advance because without their efforts, this project cannot be completed. They have my greatest gratitude. So this is the outline of this talk. First, I will give some introduction about the significance of neutrino physics and how it is related to the dark matter detectors, and then I'll lay down the formulas, including the EM properties that we're interested in, and also the initial calculation method. And then in the result, we'll present the differential cross-section and various eventuals, and finally give the constraining values. Okay, so as you might have seen in the topic, there are two portions, and first being the multi-ton CN detectors, and another being the neutrino properties. Now, dark matter detection has been a thing for decades, and in today's talk, I will mainly focus on the direct detection, which you can see is shown in the red arrow direction. This stands for time evolution direction. So we kind of assume that the dark matter can interact with the standard model matter in some manner, and if this is the direction, it kind of goes under scattering processing. So we record the reaction of the standard model matter, and then try to set the constraint on the dark matter. Now, typically, the experimentalists do this by putting a lot of liquid gases atom underground and just let them sit there and record the signals. If there are signals, they might be due to dark matter, and then we get the constraint. Now, when we see this kind of setup, we start to think, actually, we can convert this CN detectors into solar neutrino telescope. Because what we have to do is just take the background data and then use it as our neutrino signals. So in this manner, we can kind of kill two birds with one stone. So this is pretty interesting. So now speaking of neutrino physics, it is important in the sense that we know that in the standard model or in the minimal extended standard model, the EM moments, for example, a charge or the main moment, they are zero or very small, and there is still a big difference between the theoretical values and the current elements from the experiment. So this leaves a large space for new physics. One can have some conjectures or theories for the neutrinos to obtain exotic EM properties to have those kind of events. So it is meaningful to set constraint on those properties. Now, compared to what they actually do in the neutrino physics, for example, they might use some conductors and put them beside the reactive neutrino. The advantage of using xenon detectors and solar neutrino is that the ability of scaling up is pretty good. Xenons are much cheaper, and we hope that they can compensate the smaller flux of the solar neutrino. And so, but the most advantage is, of course, there is no extra setup needed. We just take the data from the dark matter detection group, and then we do our own calculation. So this is basically doing the analysis for free. And so throughout this talk, I will try to elaborate how well this goes. So the process we're considering is neutrino-induced atomic ionization. So we can write down the most general electric current, and where the Q mu is the form one transfer, and the T is the energy current. So we can identify the various EM moments, including the charge radius, magnitude moment, electric moment, and dipole moment. Now, some notes. First of all, what we're constraining is the effective moment, which means that, and this comes in for two reasons. First, that our solar neutrino is ultra-relativistic. So in this limit, one can deduce that actually we cannot differentiate the difference between the magnitude moment and the dipole moment, and they will always come together as a linear combination. This is also the case for the charge radius and dipole moment. The second is that we omit the neutrino oscillation. We constrain all flavors of neutrino as a whole. So the final, for example, the final form of the effective magnetic moment will look like this. Here is the linear combination, and we assume that it is an electric neutrino from the sun, and when it travels to Earth, it's oscillating with some, as I can say, I with the amplitude K, and then we do the coordinate sum. And then sum over the final state. So this is what we actually constrain. And so here is the list of the current best bounds. So now we only have 3 moments that we're interested in, and this is the current best bound value. Okay. So for the atomic calculation, we use an initial method called the relativistic random phase approximation, the RPA. And I will not go into detail about this, but it fully encapsulates the relativistic effect and also the atomic many-body physics. Now this plot is a result from our previous paper. It's a benchmark calculation on xenon photon absorption. Now you can see the dots here are the data from various experiments, and the black solid line is the result of the RPA calculation. And we can see that the error within this experimental and theoretical values are within 5% error throughout over 3 orders of the photon energy. So this shows that this is a good approximation, and we can carry out the following calculation with pretty good confidence. Now, and this 5% can also stand as a measure of the theoretical error of this method. Now, what we are dealing with is the solar neutrino, and the solar neutrino in this region mainly consists of 2 sources. First being the beryllium-7 neutrino and the PP neutrinos. Now this part is what I take from the Borg-Sino collaboration. You can see that the beryllium-7 neutrino is 2 discrete spikes, and the PP neutrino on the other hand is a continuous spectrum cut up at around 420 keV. So when eventually we are calculating the event rate, is that we will fold the differential cross-section, evaluate it at various neutrino energy, and then fold it with the neutrino energy spectrum here, and then do some unit conversion, and we will get the event rate. Okay. So this is the result of the magnetic moment. As you can see, the x-axis is the T, which is the energy transfer from the neutrino to the electron. And some observation can be drawn. First, the T dependence of this line here is large 1 over T. And it comes in handy because in the end, when we are doing a constraining process, we will find out that it is at the low energy bound region that it gives a higher value, which gives rendering more events. Okay. And the second thing is that we actually plot another set of line, which is the dotted line here. This is the FEA approximation, which stands for the free electron approximation. And this is different from the RPA in the sense that it does not consider the extra electrons combination and such. What it only shows is the binding effects, which appears as a step function here, we can see. And we discovered that we can see that at the high energy end, these two agrees rather well. And this is also reasonable because at high energy, the binding effect is nearly gone. So they tend to coincide with each other. Okay. And this is the plot for the mini-charge interaction. Now again, we can kind of see its T dependence now. This time is around 1 over T squared, which is steeper than the previous one. And this time we have another curve, which is the EPA curve here. So we have FEA and EPA here. Now EPA stands for equivalent photon approximation, which treats the mediate virtual photon in the EM process as a real photon. And the reason why this scheme works for mini-charge interaction but not in the magnetic moment interaction is because if we actually look into the mini-charge differential cross-sections form, there is extra 1 over Q squared in the beginning, so that the angular dependence of this process, this mini-charge process, is heavily concentrated at the forward angle, which in that place the Q squared is nearly 0, so it is more likely to more like a real photon, and that's why the EPA works. Okay, and for these two graphs, we are setting the effective charges as 1. And when we are doing the constraint or convert it into the rates, we will actually plug in various numbers, and so we can kind of like holding this line up and down, and make sure that it fits with the experimental data, and that's how we set our constraint. Okay, so this is a plot for the event rates. Okay, so there are a lot of lines here, so I will elaborate them. First, you can see the 4 lines here. The black line is the mini charge interaction, and the blue line is the magnetic moment interaction. The green line is the charge radius. Red line is the center model weak interaction. Now, in this graph, the current S-bound are plugged into the respective plot. And these 4 lines are the electric recoil events. It means that the neutrino interact with the electron. But that is not the only channel. It can also interact with the nucleus, so it renders this purple line, which is the neutrino nucleus coherent scattering. And also, we also study a few about the possible channel of nucleus scattering through the magnetic moment and charge radius channel, but their radius very low. Okay. Now there are there are 2 lines which does not affected by the values inserted here, which is the red line and the purple line. And as we can see, we shall regard this red line as a background for the electric scattering events. However, if we cannot distinguish the ER, the electric recoil and nucleus recoil event, then this purple line here will also appear as a background. So here comes in an important terminology called the threshold on the experimental side. The threshold means that there is a certain value of energy. So under this specific value of energy, one cannot distinguish the electric recoil and the nucleus recoil event. So the background becomes this line here, which is bad because we can only constrain the curves above the background. So the working space is restricted to the places above the threshold. Yeah. Okay, so here we can draw some important discussion about this. As we can see, we can already make some contribution to the dark matter detection by a better precision of estimation of the background. You can see that this line here represents the standard model with generation curve, and we can do some simple math here. If we see here, this is 20 keV, so this is 20, and this line here shoots as about 5, so it gives us 100. And if we times, this is the rate, and if we times this rate with the exposure, for example, the LZ projected has a around 15 ton-year exposure, we will get around 1,500 events right over here. So it will render an error about 2.5%, which is an improvement. And so we can estimate a better, more precise background for the dark matter detection. And this result is actually a highlight in this previous paper of the group. Okay. Now, main dish in this talk is to constrain the curves, to constrain the electromagnetic properties. And as we said, we can only constrain these to the curve that is above the threshold here. The reason being that what we actually do is we have to signal and subtract the background, and then we throw in the numbers to move these lines to fit with the data we have. So if the line, for example, the charge radius line is initially it is under the background, what we get is eventually we will have a larger value at the top. So that is not helping. Okay, so we can constrain these two. The third thing is that we see that the purple line is here, is observable. So it suggests that we can see some events of the coherent scattering of the neutrino nucleus coherent scattering. And this is also pretty exciting because the first neutrino coherent scattering is announced like about 3 years ago, and last time I checked, in this March, 2 months ago, the Coherent Collaboration announced the first detection of neutrino coherent scattering on liquid argon. So if one can see that in liquid xenon, it is also pretty good. But in reality, this threshold is not this low. It's around 1 to 2 keV. So it largely reduced the events one can see. And there are also some experimental issues. So until now, there is no news for that. Okay, so and last thing, throughout these discussions, we certainly hope that one can reach a lower background to push this forward in order to have more ability to constrain steps. Okay. So this is a plot of some result that we get. These first four rows here is the result of the current running experiments. Now we can see that xenon 1 ton can already reach an improvement on the charge radius, the mini charge here for a factor of 2 to 3 with 1 ton year exposure. And the projected Darwin can, if it gets a 14 ton year exposure, it can improve the magnetic moment by about a factor 2 and mini charge by a factor of 6 to 7. Now, this red number here is that if one can actually suppress the threshold of projected LZ from 1.5 to 0.5, then it can be seen that the constraint power will largely increase. Now, the last column here is an unorthodox setup, which is suggested by this paper here. Suggests that if one puts a radioactive source under the liquid xenon detector, and it can provide a larger flux, and then with a not bad exposure, it can improve all three kinds of moments. But if we do so, then it will completely shut the ability to detect our metal. It will completely turn into a neutrino detector, so it's kind of trick. So here is the summary. In this work, we are studying the potential using the current and future xenon detectors to constrain the resulting EM moment of the solar neutrino. And the main point is that we don't need to build our own detector, we just use the numbers from the dark matter group. So this is very efficient. And we calculate the cross-section using the RPA method. And the results show that we projected that the Darwin and LZ can have a pretty decent result on improvements of these moments here. And as expected, there is no advantage on constraining this charge radius here, because it is the background and also this T dependency. This last setup, as I just described, might do a better job, but it will result in it completely changing to the neutrino detector. So this is the selected references. Thank you for listening. Thank you. Questions? Yes. Pardon?
Page 13.
Page
13.
Oh, yeah. I'm not really sure about how you set the threshold.
Okay, so you mean this value, this thing here?
Yeah.
Yeah. So when they actually do the experiment, they have to distinguish the electron recoil signal and the nucleus recoil signal, and this is a lower energy they can go. They can distinguish these two.
So this threshold is the threshold you got from the experiment.
Yeah, we adopted from the experiment group.
So I have a naive question. You see, you actually want to probe this xenon or the axion from from the experimental result compared to your calculation. So do you assume this axiom that's with the coupling strength or the interaction only in the weak scale?
What answer?
Or how do you?
For the axiom, we have done a kind of a naive investigation on if this kind of scheme can constrain xenon, the axioms coupling by considering this similar graphs. But it turns out that the result is not good.
This is different from axiom computation, but there's one channel the axiom can be resolved by the electron. That is similar to photo absorption. Even though the coupling is not quite the same, one's vector, one's axial vector, but the similar calculation can be performed. Here, we have neutrino electron scattering, so there's a neutrino in the final state, not quite like the axiom channel.
Yeah, but it's those electrons actually is in the outer shell.
Not necessarily. It depends on the energy change.
No. So how do you model it? There are so many electrons.
Yeah, it is a so-called initial calculation. So you actually don't model it. The only free parameter in the system, the only parameter input in the system is how many electrons you need. How many electrons are there in the system? So there is no free parameter at all. And then you can get 5% accuracy for the absorption compared with data. So it's just QED.
But it's the electrons actually is bounded inside.
Yes,
The atom.
that's right.
So how do you consider this their interaction with the nuclei?
It's just Coulomb interaction.
Just Coulomb interaction.
That's right. So this is a standard atomic calculation, and it's very complicated. You need to solve it self-consistently, but you can do it with high precision. It's no problem. So I should let you answer. Why did you just mention PP neutrinos and beryllium 7? What about the other neutrinos?
First thing is that their abundance is very, very large.
Yes,
so if you can see that the flux here is, they are the highest here.
Right.
And but it depends on the, for example, if we are considering the coherent scattering, then eventually we see those two contribute to the coherent energy is actually 4. It depends on what energy scale what energy range we are looking at. So
But here it is
for the electric report, it is these two are the
I recall this since usually since this is not actually a point-like particle, it's actually an atom. So usually we have to have a form factor.
Form factor usually is used for elastic scattering. And here we can see the inelastic scattering with electron being knocked out. So we computed the ionization cross section. All right. No more questions. Let's thank Zhou again.